solutions. This is up to chapter 8, I think. So, fortunately, this stapler printed on the wrong place.
Annoyingly turned. Appreciate it. Jealousy.
Okay, so what I've not provided though is I've put the MATLAB files up yet, that we'll do hopefully today. Also the two additional questions A and B, there's no solutions written down there yet, so I thought I'd just go through them briefly now to explain that. Hopefully I'll write a description of how to solve these problems as well, but in case I don't, I'll just go through it here. Okay, so unfortunately the internet connection is down, so I can't see questions A and B. But I think I can remember what they're about, so hopefully you can as well. So question A will do with cleaning up noisy text. And the idea was that, roughly speaking, you had a set of first names. And you had a set of surnames. Okay. And so the generating process was that we were going to, first of all, we're going to just generate some kind of character at random. And then we're going to select uniformly one of these, however many were, 5 or 6 first names. And then we would go through the characters of that first name, outputting the character but corrupted possibly with some high probability. So I think there's only sort of a 30% chance that the actual correct character would be output. So it's quite noisy. And then we'd run through the whole of the first name, get to the end, and then we'd jump to sort of we just output a random character. I think we continue to output a random character with probability 0.8. And then we would jump, if we didn't output a random character, we would jump to a surname. For example, this one here, and then we would do a similar thing as before for the first names. We would run through all the letters of the surname, outputting the character, but again, potentially corrupted. Then when we got to the end, we would basically go back to the start of this whole process. So we'd output another random character, and we might jump to a first name, to a surname. So we end up with a sort of long sequence. I don't know how many, was it 10,000? Was it something like that? It was quite a long sequence of characters. So of course the point there was not to take that really long stream and just sort of see whether or not you can see David in there. I know some of you tried to do that, but that was not the intention. The intention was to think about this as more as a kind of, something very analogous to what we were doing with the typewriter, the noisy, stuffy fingers typewriter, where we used the HMM to clean up the noisy sequence. So the basic idea is that you can use a HMM to clean this up, and the HMM is going to define this generating process. Okay, so what it would be, there would be, for example, there would be a large number of latent states or hidden states. So for example, we might have a latent state for just generating noise, something like that. So before we generate the first name. We might have a latent state for generating noise, given that we've finished the first name and we're about to, but not yet started on the surname. So there'll be 2 latent states there. There'll be a latent state for each of the elements of each of the first names. So there'll be 1, 2, 3, 4, 5 here. Okay. 6, 7, 8, 9, 10. So there'll be a state for every character of all of the first names. And similarly, there'll be a state for every character of all the surnames. So I don't know how many, I don't remember how many that would correspond to in total. Probably somebody does who got it correct. But there will be however many characters are here, plus how many characters are here, plus I think we need 2 additional states for noisy character here and noisy character here. So that's, I don't know, 80 something like that states, okay. So then the idea is that your emission, so you're going to have, let's try to write this as a state transition diagram to start with. So let's say we have let's call these states. It's a little bit tricky because these states here are, this state D is not the same as that state D. It's just, so you just give these numbers. So you say call this state number, state number 1, state number 2, 3, 4, 5. And then we might have, say, this might be, say, state number, I don't know, say 31, 32, 33, 34, 35, 36, etc. Okay. So what you're going to have is you're going to have some, if you're in state 1, you have to go to state 2 because this means you started the David. So you have to go to the next state. So if you're in state 2, you have to go to state 3. State 4, you have to go to state 5. If you're in state 5, you have to go to the general state, which is just going to emit a sort of, let's call this, say, end of surname, or finished first name. Okay, so finish first name and outputs a random character. So if you're there, you have to go to this state. This state can transition to itself with probability 0.8, but then it's going to go to the first state of one of the surnames with uniform probability. So there'll be another, this is surname number 1 here. There'll be another surname here, whatever it is, the G, the graph font, or whatever. So similarly, he would go to the first state of the other surname. Okay. So similarly, so this would be a uniform probability here to go to all of the surname states. And similarly, once you go to the end there, we're going to go back to the start of this, whatever it is, say finished surname, if you like. States. So when I'm done with the R here, I've got to go back to this state here. And then similarly, when I'm here, I can go to any of the first names with uniform probability, the start of the first names. So this defines a huge, big matrix A, which is a transition matrix, which is going to be whatever it is, 80 something dimensions. Yeah. So this is the clean latent generating mechanism, and then for any state that we're in here, any probability that we're in this first name, the probability of emitting an actual character, so an observation character given some later state. So for example, if this were value number H is state 2 corresponding to the second state of a first name, well, it said that we're actually going to emit the correct character with probability 0.3. So the probability that V is equal to it emits state A, whatever you want to call that. So you'll label state A to Z, and I think there's a space as well. Is there space? No, it's just A to Z actually. So there would be 26 states for the outputs in machines. The probability that the output in A is going to be the probability that you output anything else not an A. Kind of have to write that. Everything but A. Okay. Given H equals 2 is whatever's left, 0.7 divided by however many states are remaining, 25.
Sorry, is it not that you could randomly generate the A even if you're not, even if you selected not the ideal character? Does that make sense? So you said not. It's not that you've picked the other 0.7 what it is.
Yeah.
But you could still accidentally generate A as well. Is that by chance?
Well, they're kind of the same thing.
Yeah.
I mean, they will give different slightly different probabilities.
Yeah,
That's all. So
that's what I
actually,
mean.
what I meant was I think the way it was worded was this way. But
Right.
actually,
Okay.
we probably make sure you select the correct one.
If it isn't A.
And if it isn't A, you select one of the other ones with that probability.
Okay.
I
Okay.
mean, it would just give a minor adjustment.
Yeah.
To that. But that could explain why some people's results were slightly different to what I got.
Right.
Okay, so similarly, so that explains how to do this for all of these states and all of these states. And these states here are just going to output a random character. So any one of the 26 characters you can. Okay, so that defines then your big B matrix, your emission matrix, which will be 26 by whatever it was, 83 dimensions, something like that. And then all you need to do is to run the Viterbi algorithm. So now you've got this header markup model, H1, H2, going on to H10,000. And you've got the corresponding observations now, V1, V2, V10,000. And you know what these are, and you need to now find the most likely trajectory through the latent state. Okay? And that will clean up your things. Now when you've done that, what you'll find, hopefully, is that you'll get, maybe you'll see, David there. You might see a surname. And then you just needed to count the number of times that you saw a first name. So each time you saw first name, surname, you would then add that into this matrix M and print out the matrix M. So that, I don't remember if anybody got exactly the same answer as me, maybe one person or group got that, but there were reasonable marks awarded for anything which was looked halfway sensible in the code. So I think that was, most of you got that. Okay, so it's kind of interesting. So yeah.
Sorry, another question.
Yeah.
Would you be able to share the code that you used on the Viterbi?
Sure. I can do that. So I didn't, though. I didn't solve it the way that you probably would like to see it solved. In the sense that I didn't define explicitly, the states like this. I used another piece of software I wrote myself, which is more general.
Okay.
But I can probably, what a good thing to do would be, maybe I can sort of get the solution from somebody else and maybe just post that, if that's all right. Are you happy for me to, whoever's got the correct solution, I just post that?
Because it was the code that I started to fall apart. That's
Yeah.
that's a problem.
Okay, so this, these HMMs are quite powerful objects in a sense. And so, this is a little bit of maybe a toy example, but so finding sort of strings in substrings within long strings is a very common problem. That's how we use computer science as a major problem, just search, right, just finding stuff. And the case where things are clean is interesting as well, and a solved problem. And it's very, very efficient algorithms of finding substrings within text. Right? So this is the Aho Coruscant algorithm. Maybe some of you did it as undergrads. These are sort of the cornerstones of computer science. They're really fascinating. We're actually quite complicated procedures, but they were really smart. The guys in the 1970s who came up with this. It underlines everything we do. Sort of all these searches, grep and all this kind of stuff is using all these routines. And so all of your indexing on your Windows is all done using the stuff that did in the 1970s, but it doesn't cope with the noisy case actually. This is much more relevant for things like bioinformatics, where maybe you want to say, well, I've got a sequence and I want to find maybe motifs in that sequence, but some of these things have been corrupted by some evolutionary processes. So how do you do that? You can't apply classical algorithms. So these kinds of things are heavily used in areas like bioinformatics, even though they may not view it in this way, but it's essentially what they're doing. Okay, any more questions about that one? So, the next one, question B, was to do with the guy who was drunk, moving around the station. So, it's another HMM problem. So actually, I don't believe anybody solved this problem fully, so maybe it's of interest to all of you. So just to remind you what the problem setup is. So this is the program I gave you, which is the drunk moving around the station. So the point is that you have a 50 by 50 grid here, and these green squares are people. So there are 500 people. They could occupy the same position actually, so you may not see all 500. They put two in the same place. And these people are moving randomly pretty much, or there's some structure actually to it, but they're only moving one grid square at a time, sort of the normal people. And there's a drunk, it's a little bit hard to see in red at the top. He's going to be moving two grid squares at a time. He's really going to be moving randomly. And I think the other point is that if something jumps off the grid, then it just gets sort of re-entered into the grid at a random position. Just to do that again. So you can see there's a little bit of actually a drift, so that people tend to sort of go out of the station from the central area. Okay, so now what I gave you was, I gave you a file which is like this, but I didn't color the squares. So in other words, you've got a sequence of 50 by 50 matrices with just ones and zeros in them, and the ones were just the positions of these people. So you didn't know which was the drunk, and you didn't know which was the non. And your task was to find where the drunk was. Yeah. So the solution is given by this. It's a little bit slow because it's defining a big transition matrix, and my computer's not very fast. Okay, so here we are. So this should correspond to the sequence that you actually had, because you didn't know that this was the drunk here, but I did, so I'll just color it. But the algorithm just takes this, not knowing that this is colored red, and says, well, I think that the drunk is here. So actually it's kind of correct. It doesn't get it completely correct all the time. Here it's wrong. So it's actually there, but he thought it was there. This is the most likely path. So the most likely path doesn't correspond to the actual path. But you see that it's kind of wrong there. Hopefully it will start to look a bit better. Okay, so you get the idea, right? It's kind of working. So how did I do this? Well, the idea is that we've got a position here of the drum. It's the only thing I care about. I don't really care about knowing the positions of anybody else's model. Okay, so I'm just going to have a latent state, H. And H is going to be from index, so one can be 50 by 50, because there are, whatever that is, 2,500 positions in this grid. Okay, so I want to know the position, so that's H. So I'd have HT, and the drum can basically move to some other position on this grid, which is 2 away. Okay, so he can move from, if that's position number 100, he can move to this one, whatever's within 2 anyway. Whatever is 2 away from that point. So you need to construct a very sparse transition matrix which expresses that fact that he can move to a neighbor grid 2 away. Then, if you're in this H, what does that emit to the observations? Well, they're going to be 2,500 observations, one for each of these squares. Okay, so we're going to have so if the drunk is at a particular position, say number 100, what's the probability that you will see something in good point number 1? Well, it's just some small number. If the drunk is actually at position 100, then the observation V100 will be high. It will be there with the probability 1. Okay. So what this will do is if HT is in position I, the ith observation will have a very high probability. It will actually be probability 1. All the other ones will just have the background probability of there being an observation at that point, which will be whatever it is, 500 divided by 2,500, something like that. That's just the probability a priori of there being a person in that position. Okay. So that will construct for you a kind of emission matrix, if you like. And you could then attempt to run a HMM on that, but that's tricky because you're going to have a huge 2,500 by 2,500 matrix there, which you could attempt to do and run through HMM. And some of you may attempt to do that, but you're going to run out of memory or something. It's going to be extremely slow. The other observation, though, is that these are going to be clamped, right? They're going to be fixed. You're going to observe these values. So really, you don't need to define this transition matrix. If these are given here, actually this just defines a new potential, which is going to be P of Vt given Ht, Pht given Ht minus 1. Because V is fixed, this just defines, in terms of a factor graph, some function or potential of Ht and Ht plus Ht minus 1. I don't need any more of this emission matrix. I can just define those, and I can then just use the factor graph formalism, if I like, to solve this problem. So I could say, I just need to run Viterbi max product on this factor graph, so H, T, etc. And then I just run the max product algorithm to find the most likely H. And that's what I was hoping you would do. So I think some of you did quite well. Maybe your computation fell over at this point when you tried to put it in the standard HMM. But yeah, that's it. Any questions? Okay. So this is kind of, I think the tricky thing about this question is really finding the most useful or relevant representation somehow. And you could try to solve it in other ways where you would, really try to explicitly model whether or not this is the normal person or not. You could try to do that, but it's pretty hairy because you need to, you need to have an indicator for every single one of the 500 people. And that would mean you need an exponentially large in 500, of the order of 500 to the power of 2,500 states, just to represent that HMM. So I made the number of people so big and this problem so big that that would be clearly impossible to do. So you could not solve it that way. It would never be feasible to do it that way. So that's why you had to find another representation which it was feasible. And this is really, I think, the only reasonable thing to do. Okay, good. So, that's A and B. Any more questions about the remaining assignment answers? Again, bearing in mind that I don't remember the questions because I can't get them to move. No? Good. All right. So let's move on. Okay, so you remember we were talking about learning Bayesian network structure last time. So yeah, we did this thing here. I think I realised why this has got a arrow this way actually on the previous time. I think the point is that we don't know if we know that Z and W were independent given Y and T, then we could not have had this as a collider. But that condition was searched through. It was found that the condition on T that they were not independent. And therefore that must be a collider. That's why that's. Okay, so remember we were talking about mutual information and ways to assess whether or not two distributions are actually variables are independent, given maybe some empirical data. And there are different ways to do that. So the classical way to do it, or a classical way to do it, is through this Kendall's chi-squared test with mutual information, with some sort of hypothesis testing ideas. And there's another way to do it, which is through this kind of Bayesian model testing idea. Anyway, both of these are fairly simple ways to go ahead, and the Bayesian model testing idea just is a very simple expression involving the normalization constants of Dirichlet distributions, which are simple count. Okay, so we did all this last time, and we got into this, I think. So the PC algorithm really is a kind of local algorithm in the sense that it doesn't really look at the global structure of the graph. It just looks at, say, well, these two variables here are, we think they're independent, possibly conditional upon some other local variables. And then there's a kind of a global thing at the end where you try to sort of orient the edges of this graph, sort of, so you don't get any sort of global contradictions in terms of independent statements. But fundamentally, with the way that the algorithm is constructed, is really local. So an alternative approach is what's called network scoring, where you look at the structure of the network completely, and you say, can I give some kind of score, some number to the structure of that network, which would sort of be assessing whether or not it's a good network. Okay, so as we saw last time, this is going to be tricky because there's going to be a huge number of networks. Right? There's an enormous number, exponentially large number of networks. So if I call M, say, the index for a network, in principle, M could go from 1 to 10 to the 18 for even just 10 nodes. Okay? So we're going to use a kind of a limited index to just say, this is a particular network structure that we're interested in assessing. So one of the things is that, typically if you've got more parameters, you can fit data better, right? In the sense that you've got more parameters to maximize your likelihood. So if I said in general, here's a network, and you're going to have to fit the parameters of this network, which of these two networks is going to have the higher likelihood? Well, it's going to be the network with all parameters, the fully complete network, which is the all possible parameters. That's because all other networks are sub-networks of that one, can be obtained just by somehow setting some parameters to 0. Then clearly the most complex network is the one which is going to have the highest likelihood. So that it's the same kind of similar kind of thing just in general with optimization. If you've got an optimization problem, the one which is there are sort of overarching objective function, which other objectives are just sort of special cases of that, then you're always going to get a better objective function by using the most complex model. Right? So it's the same kind of problem here. So it doesn't work. You cannot just search for the highest likelihood network. That's not in itself enough. So what you need to do is you need to constrain the problem. And one way to do that is to use this kind of Bayesian approach. So what we're interested in fundamentally is a posterior probability score of each network, so each model, given the data. And from Bayes, this is proportional to the likelihood times the prior. Now this likelihood term here, well, what's the probability that that particular structure generated the data? Now, I don't know though what the parameters are. They have to be in some sense inferred as well. But the probability of this likelihood and the model likelihood generating the data is actually given by this integral here. So normalization is the marginalization of d and theta given that. So in other words, I'm not taking the most likely parameters for a particular network and using that as a score. In some sense, what I have to do is I have to average over all possible parameters for this particular network structure, multiplied where the weighting is given by the prior probability. So I'll go into this a little bit more detail at some other point in a later lecture, but this averaging effect here actually has the property that it will kind of automatically penalize very complicated networks. This is the kind of the principle of Bayesian inference techniques, that this will not in general kind of necessarily favor the most complex network, the highest likelihood. Because in some sense you're doing a kind of averaging thing. Okay, so we need to then, for a particular structure, we need to have some parameters, and we need to put a prior on the parameters. So what it would be the natural thing for us to do, which we've already been doing with Bayesian networks, well, is to put a Dirichlet prior on the parameters, because that's what we were doing before. So then we've got a likelihood here, which is again, this is going to be conjugate. Okay, so the Dirichlet is conjugate to the categorical distribution. So this integral is going to be doable. Again, provided we make these, this usual global and local independence assumptions that we made last time, in order to make this integral factorized. So that's good. And if you do that, with those local independence and global independence assumptions, it will factorize over to all of the nodes. And the IID assumption will be factorized over data points. So for a particular network with a particular parental structure, probability that V given the parents will also all factorize. So to integrate over the parameters of that particular sort of local structure, that node given its parents, we integrate over the parameters of that using this Dirichlet distributions, and we end up with some kind of simple expression relating ratios of these normalization constants of the Dirichlet distribution. Okay. And these U's are just parameters, they're the hyperparameters of the Dirichlet distribution. So we started with some hyperparameter setting, let's call that U, and then they just get updated by the number of counts, the number of times you see the node and its parents in some particular state. Again, completely analogous to what we did in the sort of the simpler settings before. So I'm not going to go through this derivation, but you can read that in the book. Okay, so this may look a bit complicated, but the point is that for a given set of data, all you need to do is update this counts here and plug it into the Dirichlet expression there, and you've got your network score. And so that's fine. So then you can do that for any other structure that you have. So you could compare, say, two network structures and plug them into this likelihood. And if you're a priori, you don't care whether or not network number 1 is better than network number 2, a priori, then you would just use this P of D given M to score your networks. So if your pri is flat on the networks, then this is the objective that you'll use. So what we're not saying though is that we can search through all of the structures. So I cannot easily, go through all the 10 to the power 18 structures and evaluate this score for every one of them. That's not feasible. I could though, if you gave me a set of structures, which is not too big, I could evaluate them. Okay, so that's good. Another thing you can recognize about this is that the two structures actually which only differ by small local arcs in the graph, actually the only terms which will change in this product here are the terms which include or exclude the arcs. So in other words, if you make a local change in the structure of the network, we try to look at two networks which have got different structures, most of these terms will be the same for those two structures, except for where they differ. Okay, so what that means is that when you run this computation, you can avoid doing some computations because they're just the same for two structures where if the structure is shared, you don't need to rerun this computation for those shared points. You only need to rerun the computation where there's a difference in the structure. So that's just a computational convenience. Okay, so typically what people do then is they start with some structure and then they try adding sort of links in, removing links, and just see whether or not this helps to increase the probability of data given that the normal structure. Okay, so it's kind of like a local greedy kind of updating of the network. So the other question is, the only thing that remains for this is what are the hyperparameter settings? And there are different ones which people use. I typically just use the flat prior, so I just set all the hyperparameters of the Dirichlet distribution to 1. But there are some other sort of well-known settings. One's called the Biedieu score, which is some kind of informative likelihood equivalent. Okay, so this is an example comparing the PC algorithm with this sort of network scoring idea. So this graph on the left is our oracle. So we're going to generate data from this belief network. There are 7 variables. So I generate some data set, in this case 1,000 data points. So there'll be 1,000 vectors, which will be binary. In this case, is that these variables x will have 2 states, 0 and 1. So what we'd end up with is we'll end up with so x1 through to x8. So for the first data point, will be a binary vector. That might be the one sample from this network, and we'll end up with here we'll have 1,000 such samples. And given that data, I want to figure out what the network structure is. So the one in the middle is what you get from the PC algorithm, which is pretty good actually. It's just got one link here, which is wrong. I think otherwise, it didn't know what to do with this orientation here. There was a kind of arbitrariness there which you couldn't know. But otherwise, it's good. This link is also not implemented here. And actually, this one here is the network scoring algorithm using a flat prior, Dirichlet prior. Actually, this picture is slightly wrong. It's actually, this link shouldn't be there. The graph is perfect for this particular problem. And just to, I'm sure you believe me, but just in case you're in doubt, let's see if we can find it. not the world's most fastest routine. I'm slightly cheating, by the way. When this thing finally comes up, I will explain what things are doing. So maybe I'll tell you that. Okay, so what I'm going to do is I'm going to choose a particular ordering of the nodes. So I'm going to assume that I know what's called the ancestral ordering. In other words, I know that so the ancestral ordering in this case is the order of the variables. So if, say, there's a parent of a variable, that parent must have, let's say, a lower number than its child. So, for example, that's number 1 here, this number 2, number 3, number 4, number 5. Actually, so this is not in ancestral ordering because 8 is not satisfying that. But an ancestral ordering here could be x1, x2, x3, x4, x5, x8, x6, and x7. So that would be one ancestral ordering. It's only partial in the sense that you could have for this particular problem there are other orderings which are for this particular graph equivalent. Okay, but what I'm going to assume is I know this ancestral ordering. So all that means, it may not mean very much. Well, it means something, but it's not the whole answer. All it's going to mean is that we're going to have x1, x2, x3, x4, x5, x6, x7, x7. There's only x7. That's 8. Okay, so we know this. But that's, all that means is still that you've got to search in principle through all of the graphs, all of the DAGs, given this ordering. So that would be 1, that would be another 1, that would be another 1, etc. There's going to be however many words. Well, for every, we did this last time, right? For this is going to have, in principle, 2 to the power 7 possible parental connections. Perhaps this is going to have 2 to the power 6, so it's going to be 2 to the power something large, roughly 2 to the power 30 something. Okay, so still a lot to do. So I'm going to make it even simpler. So I'm going to assume that actually the number of parents of any particular node cannot be that high. I mean, in general, it's kind of strange, if you've got such a small graph like this, that to have a variable here which could have all 7 of its predecessors connected to it. That would be kind of a little bit, it could happen, but it's, I could say I don't think that's likely to happen. So I could say I just only want to search through all graphs in which there's a limited parental connectivity. So maybe each node can only have, say, I think 3 parents. Right. So then I still have quite a few things to do, but they'd be much reduced. So the reason this is chugging away is it's searching through all these possibilities. Okay. So there are still quite a lot to do, and it's evaluating then the network score for all of them. If it's ever going to finish, here it is. Okay, so this is our original oracle. So remember, this is just something that we know, and then we generate 1,000 data points from that. And this is the PC graph that we get. I think that's similar to what we had before. I mean, this is slightly, the data is randomly generated, so it may not correspond to this X problem I showed you before. And the one that the network scoring gives us is just the PC number. It's not provided there. Sorry, it's not repeat this one. So the PC algorithm itself is also not fast. Have to wait again. But you see, it was kind of feasible, but okay, it was a little bit faster. So here we go. Here is the structure that we identified from the network square, and it's correct. So of course, this isn't always going to work, right? So we can make the problem harder by having, say, not 1,000 data points. Let's say we have only 100 data points. So that's quite small. So that's not bad, but I'm just missing connections with 5. But it's not bad. It's pretty good. So if you were to rerun the PC algorithm, which is 100 data points, you won't get anything quite as good as this. So there are a couple of reasons. Obviously I'm trying to tell you that I prefer this network scoring thing over the PC algorithm for several reasons. But I'm cheating as well, right? I'm making the problem easier here because I'm saying I know the ancestral ordering, which the PC algorithm doesn't. That was not something that I imposed on the PC algorithm. And I'm also saying not only that, but I actually know the limited parental structure, which again the PC algorithm didn't know about. So I did make the problem a little bit easier. But I think you can see actually making quite a lot. Okay, so in principle, you know now how to learn structures, at least for, say, directed structures from networks. Doing the undirected case with the Bayesian thing is painful. So I'm not going to talk about that. There's something called hypergeometric prize or something. I don't know the terminology, but it's a little bit more complicated. So we know how to do it in principle, but it's always going to be hard to do. The question is though, is there other structures though which are sort of more constrained, which are easy to learn? And the answer is yes. In particular, there's a very famous one, which is called the Chow-Yu tree, and that is a tree with only at most one parent. Okay, so this is a very famous thing in computer science. So the Chow-Yu tree is a graph. It's singly connected because it's a tree. But each node only has at most one parent. Okay. So one way to think about that is to draw a singly connected distribution, which is undirected. Choose any node you like, and then orient edges away from that node in a sort of consistent way. So for example, here we chose, say, x1, the root if you like of that tree, and then we oriented edges away from consistently outside of that. So another way to do it, for example, if you were to choose, in this case, this might be a singly connected tree. If you chose, say, x4, imagine now there's no these pictures are not oriented. Okay, so this is a tree, singly connected, and you choose the x4 as the root, and you just orient edges away consistently from that. And that's a Chow Liu tree, which is a DAG, which is singly connected, which has got this maximum one parent property. So the claim is that within the space of Chow Liu trees, it's easy to learn the the most likely Chow Liu tree. But the maximum likelihood Chow Liu tree, and actually also you could do this in a Bayesian sense if you want to, is also easy to do. It's not such a big deal here with the Bayesian thing because under this heavy constraint as a Chow Liu tree, we're not going to be really over-parameterizing things very much. It's not that we're going to have one network with tons more parameters than another. So it's not a big issue, the Bayesian thing here, but overfitting. So in some sense, the maximum likelihood case is also potentially interesting. Okay, so still, there's quite a lot of networks to do here because you've got, first of all, the ordering, and there are n factorial orderings, and then for each ordering you can have at least, this could have a small number of possible links there as well. So still a large number of structures associated, but it can actually be done efficiently. In fact, it can be done in quadratic time with the number of nodes in the graph. And what I'm going to try to enthuse you about is how to construct the algorithm to do that. So this is really another cornerstone of computer science, and I'll attempt to prove this to you now. Okay, so here we go. It's a little bit, apologize, it's going to be slightly technical. So you need to be on your toes here. So, okay. The first thing we're going to do is, I'm not going to talk about fitting a maximum likelihood tree. I'm going to fit about, I give you a distribution P, and I want to find I'm going to fit a Chow Liu distribution, which I'm going to call Q, and I just want to fit it by minimizing the KL divergence. This is a more general thing than doing maximum likelihood. And we know that because we know the maximum likelihood corresponds to minimizing KL divergence when you have the empirical distribution in that KL divergence. Okay, so if I can minimize the KL divergence in general, then it's more general than doing maximum likelihood. Okay, so I'm going to do the general case first. So you're going to be given a distribution P, whatever it is, somebody comes along with that. There's no data necessarily, it's just some distribution P, and you want to fit a Chow Liu tree to it by minimizing the KL divergence between P and Q. So let's say there are D variables in the Chow Liu tree, and so we can write the Chow Liu tree Q as well as a belief network with some distribution on xi given a single parent index. So each I will have a parental index. It could be the empty set. I mean, it could be that there are no parents. Otherwise, you could have one other. So they're going to be PA of I is just the single parent index, no I. Okay, so we're going to minimize this KL divergence in P and Q. And as you know, the KL divergence is P log P, the average of log P, minus the average of log Q with respect to P. So this is the P log P term. So this term here is not going to be of interest to me because P is fixed, is given. I'm only going to be interested in minimizing the Q, so it's a function of Q. Right? So the P, the log Q term, as we saw last time by grace of the structure of the graph, the network, that the log Q will sum with the log of the product, which is the sum of the logs. Okay, so we're going to have here the average of these log Q factors with respect to P. And for exactly the same reason that we discussed last time, the expectation over P actually only requires knowledge of the variable xi and its parental variable. This is exactly the same point that we discussed last time, that if you do this marginalization, the only thing you need to, after you've marginalized over all the other variables, the only things which are left as in here, whatever that's the function. Okay, so this is our expression. There's a constant, so you're going to try to minimize this, in other words, to maximize this expression here with respect to q. Okay, so it's not a big surprise. So one way to do that is to say, well, I can add this term here, which is just a constant. It's a function of p. So I can go back to previous expression here and just add this sort of, a log p of xi given x parent of I term. So this term here, but just with p. This is a constant. I can add that on this other constant term here. What I'll end up with is essentially an average set of KL divergences. This is exactly again what we did last time to show that maximum likelihood corresponds to counting. So clearly the optimal setting is that q of xi given its parent is just p of xi given its parent. No big surprise. Okay, so that's the first thing. In fact, we already kind of intuited that. Now what we're going to do is we're going to take this setting, we're going to plug this back into this expression here. Again, this is constant, but I now know the optimal q. Yeah. The only thing I don't know is what is the optimal parent of each node. That's the Chow-Liu structure. So I'll plug that back into here, and then given the fact that log pxi gives parents is, is from base rule is the joint divided by its module here. Okay, so I can plug that back in the previous expression. Then there was some constant term, and then just here plug that in for p. Look at the minus the joint plus the log p of xi p parent and right term there. Okay. So that's a new expression. And you need to now maximize this, to minimize this expression here with respect to the parental structure. Everything else, that's the only thing which is left. Okay, so I'm going to play around with it a little bit more. I'm going to add another entropy term here in the constant with p. This doesn't depend upon the parents, the parental structure, so I can add and subtract this to the vacuous term here. And what's useful about doing that is that you recognize now that this term here combined with this term here and this term here constitutes the mutual information term. This is just another constant. So in other words, the KL divergence up to some negligible constant is just the negative mutual information between each variable and parent, summed over variables. So this, by the way, just to wake you up, in case you're suffering from motivation, was an exam question, at least for 2 years, as far as I know. Okay, so I mean, these kind of things, by the way, there should be gifts in an exam, right? Because they're just book work, so you should be able to jump for joy when you see a question like this, because it's 3 marks. So now, the only thing you need to do, again, so this is a constant, so we can forget about that. So all you need to do is you can compute the mutual informations. Right, that's something which is known for each particular parental index structure. So you need to search now through all parental structures which sort of maximize this summed mutual information. Now, because this is a tree, this thing is equivalent to the following. It's just that what we could do is we could choose a particular tree structure. We could then compute the mutual information on that particular tree. And that will give us a score, and I can always orient the tree. As we saw before, from here, if you give me a particular tree, I can always orient it by choosing a particular node as a root and orienting the edges outwards from that to give me a Chow-Liu tree. So in other words, this problem is equivalent just to finding the singly connected structure, which is a tree here. So in other words, I want a non-branching tree. Okay. So what that means is that it's equivalent to searching through all tree structures, which will give me the largest summed mutual information. With the mutual information now is going to be the mutual information between two connected variables on this tree. So if you think about it, what that means is it's equivalent to fitting a maximal weight spanning tree. Okay, so you need to search through all trees which are spanning the graph, because we need all the variables in there. Find the one with maximum weight, where the weights on the edges are defined by the mutual information. Okay, and then you need to find that one with the biggest summed weight. So it's the maximum weight spanning tree. And finding a maximum weight spanning tree is easy. We know how to do that already, because we talked about that in the junction tree. You just start with a node, and then you just find its neighbor, which has got the largest weights, and just include that node, provided that does not render the graph a non-tree. So it's just a recursive procedure. Okay, so let's saying it again. So we define this weight matrix just to be the mutual information between xi and xj, all variables xi and xj. That gives us some d squared matrix in this case. Then we find a spanning tree, a maximum weight spanning tree, according to this weight matrix. Then when we've got that tree, we just need then to arbitrarily orient the edges on it, and we've got a Chow-Liu tree. And that will correspond then to the best Chow-Liu tree we can fit to the given distribution P in the KL sense. Okay, so this is a very nice thing, right? So we've, even though there seem to be a lot of different possibilities here, we've managed to. There is an efficient algorithm to do that. All we need to do is a d-squared computation to get this matrix here. Find the maximum weight spanning tree is order d, so it's a worst order d-squared. Okay, so the maximum likelihood Chow-Liu tree is easy. We've already got it. I used slightly different notation here, but the p of x, when p of x is the empirical distribution, so I was using the indicator function before, but it's the same as delta notation. So that means that you just need to replace your p with the empirical distribution. So what that would mean is that you just need to know what the empirical mutual information between all pairs of variables, and then use that to plug into your Chow-Liu, into your maximum weight spanning tree. And you could do, Bayesian extensions thereof as well, if you wished. So this is a very celebrated result. You should try to commit it to memory. So here endeth structure learning. Okay, so it's difficult, basically. It's not easy, but there are some things which are easy-ish. Okay, so you're all very quiet today, gosh. You all hungover or something?
Coursework.
Okay, so we're going to move on to something completely different. We're going through a hierarchy, right? So we knew, first of all, everything about the distribution. So we just needed to do some kind of inference cycle. Then we said, okay, we don't know the tables, so we learned the tables. And then we said, we don't know the structure, so we learned the structure. And now, we don't even know, we're going to assume we don't even know some of the data. weird. They're going to assume we don't even know some of the data. Some things are kind of missing. So things are going to be hidden. So we're going weaker and weaker and weaker. This will turn out to be incredibly useful for machine learning. So we're going to solve all kinds of clustering problems. So all the things to do with how do you characterize your customers and databases? How do you do, I don't know, recognition of, take the internet, how do you figure out whether or not this is a web page in English or French or whatever it is, all kinds of things like this we're going to use these techniques to solve. This is going to be one of the most powerful mechanisms that we have. So we're going to have principal things which are hidden. So what I mean by that, I mean that you could have some data, a data set, but maybe, for example, you've gone out and you've got some questionnaires, but not all the people responded to every question. So you don't know how to what to do with that. So there's a kind of question mark in the data. Other times when we make a model of the situation, we could have, in principle, things which are just never going to be observed in the data set. So, yeah, so maybe I'll give you an example about this. So think about something like physics, okay? We're going to try to predict the weather. It's like a hidden Markov model. In a hidden Markov model, you've got this latent variable which might be something to do with the state of the weather, maybe, right? The pressure. But you never really, you can't observe that. You can only observe something which is a function of that, like some kind of whether or not it's raining at some particular weather station. So given the observed things, you want to then infer what is happening with this latent system and use that to predict what's going to be in the future. And that's actually what they do. So the whole meteorology is about solving, in some sense, HMMs. Okay? Just doing inference in HMMs. Very, very large scale HMMs. So other things you might think about are, you could have, say, like, say a car, okay? Like, but this car has got some complicated model for its engine, and the engineer comes along. We cannot get into the details of the engine. Maybe you can measure the vibration of the engine or something like that. You can then infer that there's some particular problem with the engine. So latent variables, we're kind of familiar with them. But for all the problems that we've seen so far with HMMs, I told you how to learn the tables, or somehow I even gave you the tables. I said, for this particular tracking problems, the tables are actually given for you. Right? The transition matrix A and the emission matrix B were given. But let's imagine that somehow now you think it's suitable to have a latent variable structure like a HMM to model your problem. That's your intuition. But nobody tells you what the transition and emission matrices are. They just say, this is the data I have, this is the time series of observations I have. Please tell me what the A and B emission and transition matrices should be. Okay, so how do you do that? And these are the kinds of problems that we're going to look at here. Okay, so to be a little bit more concrete, let's imagine we go back to the asbestos smoking cancer network. So in that case there we've got, under IID assumptions, each data point V is 3 variables asbestos smoking cancer, given some table theta, and it just factorizes the cancer given asbestos smoker, asbestos smoker. Okay, we figured out how to learn by maximal likelihood or even Bayesian methods what these thetas are of this table, this table, this table. And using this global and local independence properties, it was great because it meant the whole thing factorized posterior over these thetas, factorized into each of the individual ones. So things were fairly straightforward. Now though, let's think about the case where we never know whether or not somebody has got cancer. Sorry, it's a smoker. Okay. Sorry, this is whether or not they have asbestos. So you don't. So you're only going to measure. So you only know in the data set whether or not somebody is a smoker, whether or not they've got cancer. You don't know whether or not somebody's asbestos exposure. So this is, it's important to include this modelling effect because you think that asbestos is an important part of the process, but unfortunately you don't know whether or not this particular person has got that. So the question then is, how do you learn the tables without that knowledge? Well, we can only maximize the observed data. So one thing we could do is say, well, even though I don't know what the asbestos is, I could just maximize the likelihood of the things I do observe, which is, in this case, smoking and cancer. So I could sum over the space of asbestos, and that would give me the likelihood for the visible variables smoking and cancer. Okay, so it's given by this. Now, because of this sum, this thing now is not anymore a product of a function of theta c times by theta a times by theta x. Right? So, because I've got a sum here, it's a sum of products. So if I take the IID assumption and I product this over n, over the data points, previously we had when everything was observed, we had a product in here, product in here, right here, but now I've got product of sums. So this means this whole thing, this functionally, is no longer going to factorize into some function of theta c, some function of theta s, into some function of theta a. So it's going to be a real dog's breakfast, unfortunately. There's no simple thing we can do anymore. So that's why maximum likelihood itself is going to be tricky to do this. We're not going to be able to do this decoupling. And the same is going to happen for the Bayesian thing. When we did the Bayesian thing before, the posterior factorized nicely. And it's the same problem here, the posterior, because now you're going to have a marginal posterior by summing over A, and simply you're going to get a kind of corresponding coupling between parameters. So no amount of parameter independence a priori is gonna give you a factorized posterior, so you're in trouble again. So what this means is that for this particular problem, the issue is not so much one of, it's not a conceptual issue. How do you do this? What is the how do you solve this problem? It's a computational issue. So the answer is we're going to use maximal likelihood. Conceptually, it's easy. But computationally, it's difficult. How to find the optimal maximum likelihood? We'll have to do it in a Bayesian way. We're going to struggle with that. Okay, so let's look at another sort of motivating thing. So we're going to stop men on the street, and we're going to ask them their favorite color. Is it blue, green, or pink? Okay, so the point is that what's going to happen in this particular thing is that for men whose favorite color is pink, they're going to refuse to answer the question. So there are more, you can think about this also in terms of voting. So if you do elections and you ask people after the election, what did you vote for? They're not usually going to respond if they voted for some extreme party. So this is the kind of analogous problem. And then the question is, what is when you've collected all this data, what is the probability distribution for men's favorite color? Well, one way to do it is to say, well, I just throw away the data, which where I don't have anything. So I'm going to have blue and green, and basically what's going to happen is you have the log likelihood of the blue under IID assumptions, log likelihood of this, times by some likelihood of the green. So let's say there's in this particular case you ask 3 people actually. So one person says they like blue, one person says they like green, another person doesn't answer. Okay, so you throw away this person doesn't answer, say log theta to the probability of blue, log theta to the probability of green, and this is just you could do this by Lagrange terms, because you just need to ensure normalization, such that the theta b plus theta g plus theta p, blue, green, and pink, you just sum up to 1. So if you maximize this expression now, including this Lagrangian term here, what you'll end up with is the probability that people who have like blue is a half, like green's a half, and the probability that pink is 0. Because you've not included anybody, the two like blue and pink equal, blue and green equal. But that's clearly wrong, right? Because if you know the reason that men are not answering this question is because they're embarrassed, so that they call it pink, then you know that's a different mechanism. If you really know that, then you need to do something else. You need to include that mechanism. So you could say, well, you know, the probability. I need to model probability that the data is actually going to be missing as well. In this particular case, if you know that the probability is missing, it's just the probability essentially if it's going to happen if the man is light pink. The probability the data is going to be missing is just the same as theta p. So in that particular case, you can say, well, actually, you know, the data set is not just one blue, one green. It's one blue, one green, and no response. That's not the same. And if you know what the mechanism of no response is, which we assume we'll do here, and you rerun that case, and then clearly what you get is 1/3 to each of the three things, which is what you'd expect. That's the kind of the right answer. Okay. So there's something I'm not going to talk much about, but the question, there is some conceptual issues a little bit about what is, when can you use the likelihood, maximizing the likelihood of observations as a kind of a bona fide method for actually learning parameters. And there are some problems to which that's not in itself the correct thing to do, and we're not really going to discuss them here, but you can read them about them in the book if you want. But the basic point is, as long as there's a kind of like, there's nothing really coupling the data mechanism too strongly, then we can just use maximum likelihood of the data. All right, so the general setup will be, we're going to use maximum likelihood on the and in general in the observed data, and we're going to marginalize or integrate out over any hidden variables. Okay, so we want to then maximize this probability here. So one algorithm we're going to try to do now is called the EM algorithm. And the EM algorithm will be one way to, it's a computational device to try to help us find the theta which will maximize this marginal likelihood. So I want to really hammer this home, because this sometimes gets really lost, I think, in the big picture. But the EM that we're going to discuss now is one way to do maximum likelihood learning of when you don't have, when you have hidden variables or latent variables or missing data. It's not the only way to do it. Okay. You can use whatever you like, to maximize this likelihood. Gradient methods or whatever your preferred optimization routine is. The EM is a particular mechanism which was introduced in the 1970s for doing this, to some widespread skepticism. And indeed, it turns out that EM is a great algorithm, but it's not always the best thing to do. And indeed, there are many cases where EM is a really terrible algorithm, and you would not be recommended to use it. Okay, don't think every time you see a latent variable problem, I have to use EM. It's not necessary. But yeah, when the first paper came out, published on this, people said, we don't see the point. And indeed, for that particular problem, there was no point. It was really a poor algorithm. So I apologize again, this is going to be fairly technical. So do you want to have a break now? Or do you want to go through it and have a break after? You want to have a break now?
Yes.
Okay, so let's come back in 20 minutes.
Food.
Got no